Hello, today I will be presenting my honours research project in which a learn heuristic approach is taken to solve a constrained, multi-objective portfolio optimization problem. For this project, I was supervised by Prof. Terence Van Zyl and Andrew Pascaramudi. Multi-objective portfolio optimization problems that aim to maximize returns and minimize risk simultaneously by using unconstrained models are fully capable of producing optimal solutions on an efficient frontier. However, such techniques pose challenges when considering realistic portfolio problems as they fail to consider constraints such as transaction costs and holding costs, which cannot be ignored in realistic trading scenarios. Therefore, we propose to introduce these realistic constraints into a multi-objective portfolio optimization problem, for which learn heuristics will be used in order to demonstrate which algorithms produce optimal results. Metaheuristic algorithms assist in solving non-convex problems. The algorithms explored in this research are those of the evolutionary algorithms, namely NSGA-II, R-NSGA-II, NSGA-III, and U-NSGA-III, whereas the machine learning models used to enhance these metaheuristic algorithms are that of the surrogate-assisted variants of each metaheuristic. In the literature, researchers compare different machine learning and deep learning models with portfolio optimization models. In the end, an effective strategy is found. However, the only issue is that a high turnover results in a huge challenge for these models to overcome, as this implies that the transaction costs will be quite high as well. Therefore, this project introduces them as constraints into a portfolio optimization problem by means of learnheuristics. Learnheuristics is a hybrid approach that combines metaheuristics with machine learning or statistical learning models. In this research, we pair each of the four multi-objective genetic algorithms with a surrogate model, which will then be used to evaluate the portfolio optimization problem. Surrogate models can be incorporated to accelerate the convergence and approximate the time-intensive functions of other models and algorithms. The implementation of this research can be separated into 5 main interdependent sections. We begin with the data cleaning and exploration process. The dataset used in this research is that of the S&P 500 index and originally contains 619,040 rows and 7 columns. In order to clean and pre-process the data, we change certain data types and create a new data frame which eliminates redundant attributes. In addition, all duplicate, missing, and null values are dropped. For this research, we only use the top 10 stocks with the highest expected returns as our portfolio. Next, we move on to forecasting. In order to forecast the data, some form of noise needs to be added. To do this, we simply acquire random samples from a normal distribution. This outputs an array containing white noise, which is added to the data, resulting in forecasted data values. In this research, the genetic algorithms are needed to satisfy 2 main objectives. The first objective is optimizing the portfolio and finding the optimal constraint value simultaneously. To do this, we create a class for the objective function in which we find optimal portfolios and produce an efficient frontier. Then, we search for the best possible constraint parameter with the aid of a callable lambda function and maximize the Sharpe ratio. The second objective is producing the best set of weights for each asset. Within the objective function, we add an objective to the efficient frontier, which consists of a parameter for L2 regularization. The genetic algorithms search for the best possible value of gamma, which in turn produce the optimal set of weights that are used to perform backtesting. This process is heavily dependent on the PyPortfolio Opt and PyMove frameworks. Next, we adjust each of the functions to include a surrogate model from the PySmooth framework. We manually fine-tune the parameters until we are able to see that the surrogate-assisted genetic algorithms are learning throughout the iterations and eventually produce an optimal solution. The genetic and learnheuristic algorithms are respectively run 10 times on a population size of 12 over 30 generations. The average time taken and average hypervolume is recorded at the end. Lastly, we run simulations or backtests in order to help optimize our strategy. We first run a backtest using the portfolio backtest library's built-in method of determining the weights for each asset. Then, we use each of the 4 learnheuristic algorithms to search for the optimal set of weights that can then be passed into the backtesting function. Based on the results, it is evident that the NSGA-II algorithm takes the longest time to run. However, given that it produces the highest hypervolume, it suggests that it is the best performing algorithm. From Figure 1, it can be seen that the NSGA-II algorithm is also the first to converge. Next, we present the results of the 4 learnheuristic algorithms. Table 2 indicates that, similar to the non-surrogate variant, the NSGA-II learnheuristic yields the highest hypervolume, making it the most efficient algorithm. Figures 2 to 5 each indicate that the learnheuristic algorithms produce higher hypervolumes and converge sooner compared to the baseline algorithms, despite taking significantly longer to run to completion. Based on Table 3, we see that the learnheuristic algorithms outperform the backtest run without learnheuristic algorithms. The portfolios that run by utilizing the surrogate-assisted genetic algorithms to find the optimal weights for asset allocation yield higher returns for a lower percentage of risk and also produce greater Sharpe ratios. Based on these findings, we are able to conclude that the learnheuristic algorithms outperform the baseline algorithms in terms of hypervolume and rate of convergence, although they take much longer to run to completion. Overall, using learnheuristics to obtain the weights of each asset for backtesting purposes results in more preferable results compared to backtesting without using learnheuristics. The learnheuristic algorithms are sensitive to many of the input parameters. Therefore, in future research, implementing a search algorithm, such as a random search or a grid search, to tune the parameters would be beneficial. This may also assist with allowing the learnheuristic algorithms to consider portfolios with more than 10 assets and still produce optimal results. To conclude, I would like to acknowledge and thank my supervisors, Prof. Terence Van Zyl and Andrew Pascaramuthi, for their invaluable assistance with my research. Thank you for your time. The full research implementation is accessible on my GitHub repository, and if you have any queries, please feel free to send me an email.